But apparently it's brilliant.
You're like the paradox one, is it? The parallel universe one, where they just explain like it was like doing math and it's like the Schrodinger equation and everything. Like I was like, wow, this is actually.
I feel like I've seen parts of that one.
Yeah.
I should look that one up because I feel like I've seen parts of it.
Yeah.
Cartoons for thinking people. Sort of. Okay. Alrighty. Now let's look at CV. Because we're trying to find gamma derivation. Oh. Well, we've got CV, let's find CV. Oh, no. Oh, wait, no.
Refreshing.
Yeah, indeed. Note that for constant NA, du is CV dt no matter what. Since u is CV times t, right? In other words, CV was 3/2 NAR, and U was 3/2 NART, so U is CVT, so DU is CVDT, no matter what, as long as NA is staying constant, so that you don't have to worry about a dNA term in there. So in other words, if we find the specific heat at constant pressure, CV, that'll be dQ dt at constant pressure, I'm sorry, du dt at constant pressure plus, well, I'm skipping a piece here. I did mean dQ dt at constant pressure, sorry, which will be du dt at constant pressure plus P dV dt at constant pressure since dq is du plus P dV, and du dt at constant pressure will still be CV, in other words, because du is CV dt no matter what. So we get CV plus another piece due to the P dV dt term. So we have to figure out what that second term is, but in other words, CV is CV plus an extra piece. And the reason for that is that if I have my cylinder again, so imagine that I turn on a burner under that, but I lock the cylinder in place. I don't let it move. Would I be, in that case, if I measured how much heat had to flow in order to raise the temperature by 1 Kelvin, and I lock the cylinder in place, would I be determining the heat, specific heat at constant temperature? That doesn't make sense. Specific heat at constant pressure or at constant volume? Constant volume, right? Because I'm not letting the volume change. So CV to measure CV, lock cylinder down and add heat until until T rises 1 degree, rises by 1 Kelvin, or 1 degree Celsius, take your pick, they're the same thing. Now, if I do it at constant pressure, well, first of all, so if I do that, what's going to happen to the pressure inside the gas while I'm making that measurement? It's going to go up, the pressure is going to rise, right? So the pressure would rise inside there. So if I do this at constant pressure, then I have to not let that happen. How do I not let that happen? I unlock the cylinder and I let it keep expanding so that it's always at the pressure inside is always equal to the pressure outside. So what will the cylinder do when I unlock it? Will it, as a result of that, as I start adding heat to it, will the cylinder tend to rise or fall?
Rise.
Or sorry, the piston will rise, right, because the pressure is piston cylinder. The piston will rise because of that. So the gas inside, is work being done on it, or is it doing work on its surroundings? If the piston's rising, is the pressure inside the gas doing work on the surroundings, or is it the other way around?
It's doing work on the surroundings.
It's doing work on the surroundings. So in other words, when you have the specific heat at constant pressure, some of the heat is going into raising the internal energy, but some of the heat is going into that work done on the surroundings. So you need extra heat to raise the temperature at constant pressure because you're wasting some of the heat by doing work on the surroundings as the gas expands. And that's why the specific heat at constant pressure is bigger than the specific heat at constant volume, because at constant pressure, you're also doing work on the surroundings as you add the heat. It takes extra heat to do it. So we'll say, but to measure Cp, we unlock the piston. So that the gas in the cylinder can expand and keep its pressure equal to the surroundings. Which means some of the heat input is, you can kind of say, wasted on PdV as opposed to du, so to speak. You have to also do some PdV work in addition to increasing the internal energy when you add heat at constant pressure. We're treating this as an ideal gas. Since for an ideal gas, we have the ideal gas law, PV is nRT, we're doing everything per unit mass, so NA-RT. NA here is the number of moles per unit mass as opposed to just plain the number of moles. So P times the volume per unit mass is equal to the number of moles per unit mass times RT, is what this is saying. At constant P and NA, P times dP dt at constant pressure is NAR. Just take the derivative of both sides with respect to temperature, keeping the pressure constant. So there's no dP dt because the pressure is constant. Take the derivative of both sides with respect to T, but there's no dP dt term. There's no vdP dt term because the pressure is being held constant. So P dV dt at constant pressure is NAR. So now we know what to put for that extra piece. P dV dt at constant pressure is NAR. So Cp is equal to Cv plus NAR. Boom. Ideal gas, constant Na. That was used in our derivation. For an adiabatic process, dQ is equal to what for an adiabatic process by definition? 0, yep, no heat flow. dQ is equal to 0 by definition for an adiabatic process. So that says du is minus PdV if our process is adiabatic, because in general du is dQ minus PdV. dQ is 0, so du is minus PdV. In other words, we're only going to work on the surroundings to change the internal energy. No heat is coming in or out. But from the ideal gas law with constant Na, ideal gas law PV is NART with constant Na. But now I'm not assuming that either P or V stays constant here. I'm assuming dQ is 0 in this case. Well, then we can take differentials of both sides. The differential of PV is PdV plus VdP. So PdV plus VdP is equal to NAR dt. If Na were changing, I would also need an RT dNA term, but we're keeping Na constant. dt is du over Cv, because remember that du is Cv dt. Cv being 3/2 Na bar, so dt is du over Cv. And if it's adiabatic, so that du is equal to minus PdV, this is equal to minus PdV over Cv. We have for an adiabatic process, plus VDP is equal to minus, parentheses, NAR over CV PdV. In other words, here I've substituted dt is du over CV, but that's minus PdV over CV. So I've substituted that on the right-hand side. Happy? Not happy? Everybody happy? Okay. So now we've got two terms that both have PdV in them, so let's bring them together. They'd be happier with each other. And let's bring the VDP over to the other side. So this says that P times the quantity, 1 plus NAR over CV times dV is equal to minus V dP. So this says then that CV plus NAR over CV times dV over V is equal to minus dP over P. In other words, I put everything with P on one side, everything with B on the other side. And so in other words, I pulled this V on the right over to the left by dividing through. I pulled this P on the left over to the right by dividing through. And then 1 plus NAR over CV can be written as CV plus NAR over CV, because then the CV over CV gives 1. And in other words, what I've done now is I've separated the variables so I can integrate both sides. If this is a separable differential equation, I can integrate both sides. But first, let's note, what is CV plus NAR? That's CP. That is CP. That's CP, so I've got CP over CV, which we call gamma. So gamma times dV over V is minus dP over P. Remember, we defined gamma to be the ratio of specific heats, CP over CV. As an aside, ideal monatomic gas, which is typically what we're dealing with in a stellar interior, they don't have molecules, then gamma will be 3/2 NAR plus NAR over 3/2 NAR. Or in other words, this will be 5/2 NAR over 3/2 NAR. Equals 5/3. So typically for us, gamma will be 5/3 because that's the ratio of specific heats for an ideal monatomic gas. We'll just leave it generically as gamma, but keep in mind 5/3 is the typical value we'd be dealing with. 2, 4, 6, 8. Now we want to integrate. Integrate both sides. What's the integral of dV over V? Natural log V. Yep. So on the right here, we have gamma natural log V is equal to minus natural log P plus some integration constant, I'll just call it capital A, Okay? Now what am I going to do?
Bring it on over. Okay.
We could do that. You're absolutely right. I'm going to do, instead of bringing it over, I'm just going to do it a different way. 2, 4, 6, 8. Now we want to exponentiate, right? This is natural logarithms. I started saying exponentiate. I suppose that was your cue to say it, right? Totally botched it.
Hold up.
Yeah. It's like, don't tell anybody the secret that Mrs. Higginbotham has been seeing Mr. Oh, oops, you know. Anyway, 2, 4, 6, 8, time to exponentiate. So this says e to the log v to the gamma, because e to the gamma log v is the same thing as e to the log v to the gamma. Right? E to the a b is e to the a to the power of b is equal to e to the log p to the minus 1 times e to the a, is e to the a plus e to the x plus y, e to the quantity x plus y is e to the x equal to y, so I've just exponentiated both sides and written it in that form, because then e to the log v, of course, is v. So this says v to the gamma is 1 over p, because e to the log p is p. So p to the minus 1, in other words. So v to the gamma is equal to e to the a times 1 over p. Or in other words, p v to the gamma is equal to k, where k is a constant. It's e to the a here, but let's just rename that k, because what was a? So and in fact, what that constant is going to depend on is the entropy per unit mass S. So we're doing everything per unit mass, which won't be particularly important to us. I'm just mentioning the constant's actually set by the entropy per unit mass. This is the adiabatic gas law. That's the adiabatic gas law. In other words, the pressure times the volume to the gamma stays constant for adiabatic processes. It's still true, PV is nRT as well, but also, if it's adiabatic, no heat flow in or out, then another way to put it would be that P1 V1 to the gamma is equal to P2 V2 to the gamma, would be another way to put it, because that product stays constant. So if I change the pressure from P1 to P2, I can get the change in the volume from the relation that the corresponding change in the volume will have to satisfy the P1 V1 to the gamma is P2 V2 to the gamma. Because they're both equal to the same value, they're both equal to the same constant K. And then remembering that the RV is the specific volume, the volume per unit mass, 1 over the density, we also have P rho to the minus gamma, I'm sorry, P rho to the minus gamma is equal to K. In other words, V to the gamma is 1 over rho to the gamma. It's rho to the minus gamma. Or in other words, another way to write the adiabatic gas law is that the pressure is a constant times rho to the gamma. Again, the constant depends on the entropy. So remember that our adiabatic process, it's still an ideal gas. It's still P is NKT, PV is NRT, all that kind of stuff still holds. But we've got an additional constraint, an additional relation, because no heat is flowing in or out, that if I know the pressure, if I know the entropy, that tells me K, and the density and the pressure are linked by this relationship if the process is adiabatic. But another way, you could have said P1 rho 1 to the minus gamma, or P1. You could also say, in other words, P1 over rho 1 to the gamma is P2 over rho 2 to the gamma. So if I have gas in a cylinder and I measure its pressure and density, if I allow it to change its density or pressure adiabatically, this relationship will tell you how the other quantity changes. If you change the pressure or the density, this will tell you how the other quantity changes when you do that, if it's an adiabatic process. So from our last relationship here, P is K rho to the gamma, we can write that the logarithm of P is equal to the logarithm of K plus gamma times the logarithm of rho. Now let's take DDR both sides. Remember, we're inside a star here, so let's see how both sides change with respect to radius. Well, first of all, note that the derivative of the natural logarithm of P with respect to R, by the chain rule, that's d log P dP times dP dr. And what's d log P dP? What's the derivative of the logarithm of P with respect to P? Natural logarithm is the function whose derivative is 1 over P. Yeah, 1 over P. Yep. Right. How did that work again? Right. Yeah. Yeah. The logarithm differentiates to 1 over P. So the derivative of log P with respect to R is 1 over P dP dr. Similarly for log rho, that's 1 over rho d rho dr. So we get that 1 over P dP dr is equal to gamma times 1 over rho d rho dr. So dP dr is equal to gamma times P over rho times d rho dr. If it's adiabatic, the pressure and density derivatives are related in that way. So now let's write the ideal gas law, which again, our adiabatic gas obeys the ideal gas law too. It's not that there's not a choice between ideal gas law and adiabatic gas law. It's that an ideal gas also obeys the adiabatic gas law if there's no heat flow in or out of the gas. So remember, one of our ways to write the ideal gas law was P equals rho KT over mu mH. Well, 2, 4, 6, 8 times 2 logarithmiate. Let's take logarithms of that. Log P is log rho plus log T plus log everything else. Log K over mu mH. And now let's differentiate this with respect to R. So if mu is constant again, we don't have to worry about ionization. If mu equals constant, we have that one over P dr is 1 over rho d rho dr plus 1 over T dt dr. The other stuff is constant, so it doesn't contribute to the derivative. You can get this directly from this relation, but I think it's easier to take logarithms first. It drops right out if you take the logarithms. So this says dp dr is P over rho d rho dr plus P over T dt dr. Smile. And then notice P over rho d rho dr is 1 over gamma dp dr from equation smile. Just dividing through by gamma, P over rho d rho dr is 1 over gamma dp dr. Worth noting this is for an adiabatic process. In other words, here's generic, throw in that it's adiabatic, and we can substitute for that term for an adiabatic process. So the adiabatic temperature gradient, which is what we're after here, we can get by substituting in this equation right here. We've got dt dr here. After we put in the adiabatic business, both the other terms involve dp dr. So we can rearrange this to say dTdr adiabatic is equal to the quantity 1 minus 1 over gamma times T over P times dPdr. Just rearranging that expression over there. Again, P is rho KT over mu MH, ideal gas law. So T over P is equal to mu MH over rho K. So this piece right here can be written as mu MH over rho K. And now we go way back to hydrostatic equilibrium. Which said that dPdr was minus rho acceleration due to gravity, but the acceleration due to gravity is g m sub r over r squared. So that was hydrostatic equilibrium. The pressure gradient is minus rho times the local acceleration due to gravity. So we can substitute that for dPdr, this for T over P gets this substitution, dPdr gets that substitution. And this gives us what we want, the adiabatic temperature gradient. The adiabatic temperature gradient is minus 1 minus 1 over gamma, which of course you could write as gamma minus 1 over gamma if you wanted to, times mu mh over k times g m of r over r squared. This equation gets a box, and the designation, that's equation 4b, because remember that 4a was the radiant temperature gradient. So with, like a page or so of derivation, we got equation 1. With a couple of lines, we got equations 2 and 3. Another page or so gave us 4a, and then a notebook gave us 4b.
An entire lecture.
Yes, 2 lectures really, because I was,
Doing it last
I
time.
started it last time, so 1 plus lectures gave us 4b. So that took a while, but we learned a lot along the way, and we feel good about ourselves. And we feel good about ourselves. Yay! And there's much rejoicing.
Maybe later.
Maybe later.
Right. That's okay.
So, yeah. Well, that's like a Saturday thing, because you're so long, it's not fair.
My plan is not to sleep.
My plan is to die.
That's a good look.
So, let's put all this in terms of our condition for convection. That's the temperature gradient if there is convection. to a good approximation. It's actually the adiabatic temperature gradient. The actual temperature gradient needs to be a little bigger than that to make convection happen. But that'll be our approximate temperature gradient when there's convection. But we still haven't said, okay, well, how do I know when there's convection? So let's complete by saying that. Since dTdr is less than 0, right? In other words, temperature is decreasing as you go higher up away from the center of the star. The condition that the actual temperature gradient in magnitude is steeper than, larger than, the adiabatic temperature gradient becomes when you remove the absolute value signs, it flips around, right? If the absolute values are greater, but if one side is greater than the other side, but they're negative, you have to flip it around. Like for example, the absolute value of -3 is greater than the absolute value of right, -2, right? But on the other hand, -3 is less than -2. So when the quantities involved are negative, when I take off the absolute value signs, I have to flip the direction of the inequality. So this becomes that, in fact, in terms of the actual values, using negative numbers being smaller when they're bigger, so to speak, the adiabatic temperature gradient is less, the actual temperature gradient, I say, is less than, more negative than, the adiabatic gradient. So what we want is the actual temperature gradient, dTdr, to be less than the adiabatic gradient, which we'll put back in this form again. This was the adiabatic temperature gradient. We rewrote it into this, but now I'm going to put it back in this form again. dTdr needs to be less than 1 minus 1 over gamma T over P dTdr. Or 1 over 1 minus 1 over gamma is greater than T over P dPdr divided by dTdr. So I flip the sign again. And that's because dTdr is negative. So when I divide by a negative, it reverses the inequality. dTdr is less than 0. So we reverse the inequality when dividing through by it. Now this is legitimate. It's an example of what my freshman year college calculus professor called bad algebra but good calculus, pretending that you can treat differentials as regular algebraic quantities. It's legitimate to say that dPdr over dTdr is dPdr times dr dt, or in other words, that it's dp dt. It's legitimate. That's an application of the chain rule. You're allowed to do that. in other words, now we say that rewriting the left-hand side there, gamma multiplied by gamma over gamma, to get gamma over gamma minus 1 is greater than T over P dp dt. Or in other words, it's dp over p divided by dt over t. Which is the differential of the natural logarithm of p divided by the differential of the natural logarithm of t, because the differential of log p is dp over p, because the derivative of log p is over p. So last thing, before we have the sorrow of parting with this class for today, is now we have the condition for convection. The condition for convection to take over the transport of energy instead of radiative diffusion. My phone is sad that we're ending class because its battery's down to 25%. So I'm just going to let it cry us out here because I don't want to turn it off with my chalk-filled hands. I have to play a sad and mournful tune when the battery is below 25% so that I remember to turn it off. It's saying, I'm hungry, instead of radiative diffusion. Whereas when the battery's full, it plays this happy like, dum, 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 dum. And anyway, this is ridiculous.
Something is like the sad ending to a long story.
I know. That's what gets the box. D log P, D log T is less than gamma over gamma minus 1. This is hard to continue. Remembering for our ideal monatomic gas, gamma is 5/3. This gives us that gamma over gamma minus 1 is 5/3 over 2/3 equals 5/2. And that's a funny looking thing, d log p over d log t. But really, that's just compact, somewhat weird notation. D log p over d log t, d log p, d log t is just p over t, dp, t over p, dp dt.
Sounds like a buffalo died.
What?
He said it sounds like how the buffalo died or something.
Yeah. The end.
Roll credits. Where was your phone?
It's in my pocket.
Oh, that's
Which is why, like my other pants, it's worse, but you're beginning to see the outlines of my phone case on my pocket here.